Hello from the Forcetronics YouTube channel. Welcome to how to build a simple DC electronic load with Arduino. And this is part 2 in a series of 2. If you haven't seen part 1 yet, I recommend you check that one out first. Before we get started, I'll mention if you need Forcetronics contracting services or manufacturing services, check out forcetronics.com. Also, if you like what you see here, check me out on Facebook, Twitter, and subscribe to the YouTube channel. All right, let's get started. Okay, here's our setup for part 2, and if you notice, it's very similar to part 1, but we added measurements. So the wiring in blue in this schematic is to show the parts that were added. So we still have our core piece, which is our DAC. I'm using Arduino 0, so A0 is a DAC output, digital analog converter. We use that to control the voltage drop across this load resistor, and hence we can use it to change the input current from whatever we're testing, whether it's a power supply, a battery, a solar cell, whatever. Okay, so to measure the voltage of the input, or the DUT, device under test, we are running A2 to the input. What I did here is I'm just using the Arduino Zero's basic setting or default setting for ADC measurements, which is its own power supply, VCC 3.3 volts. So that means my ADC is limited to measuring 3.3 volts. Now, if you want to change that, what I did here is I put in a voltage divider network. And we can use, if we know the exact values of these resistors, which I measured with a high accuracy digital multimeter, we can then calculate what the voltage will be. So once again, these are added so we can measure higher than 3.3 volts. I really want to use this to evaluate lithium ion or lithium polymer cells. So what I did here was I basically set it up so I can get well above 4.2 volts because that's around the highest charge rate of these cells. So I'm almost at 5 volts. Now, once again, you can see the formula I used here. Once again, just a resistor divider network. This tells us how we're going to use this to make our measurements and how we convert it into voltage, and we'll see that in the code. But you can change these values to whatever you want to ensure you get the voltage range you're looking for. Next, I'm using A4 to measure the current. And so what we're really measuring is the voltage drop across the load resistor. If you know the exact value of your load resistor, we can then use that to calculate the current. All right, so that's the main thing we added to the hardware, but we did a lot in the software. Now let's look at some of the measurement features that we added in the code. Then we'll take a look at the code. Then we'll take a look at the hardware setup, and we'll see everything tied together in some examples. Okay, so here's a quick overview of the added measurement capabilities. So 2 types of voltage and current measurements. The first is a fast sampling measurements. So we'll be able to almost, I don't want to say digitize, but close to digitize the voltage and current so we can see the voltage in real time, and we can see the current shapes, or I should say the current profile of the device we're testing with fast current measurements or fast voltage measurements. But we also have average measurements for higher accuracy. So let's say you're working with a load that has a steady output, we can do the average measurements. But beyond just the average measurements, we're going to show that we can adjust the measurement rate, so we can change how fast we're doing the fast measurements or how many measurements are included in our average measurements. We also have amp hour measurements. So if you're evaluating a battery, you can, while you run the electronic load, you can make amp hour measurements so you can see, okay, if this is going to be the current profile of my design, I can see how long this battery will last. And then also we have min and max measurements. So this goes along with the average measurements. We can pull out the min and max and display those. So those are some of the measurement features we added. Now let's take a look at the code. Okay, here we are with the code. And one thing I'm going to mention right away is I set this up so everything can be read through this serial plotter, the serial monitor. Now, if you want to polish this off or make a finished design, you probably want to do some kind of UI, whether it's a touch screen or an app, or I don't know, even sending it to the cloud, like using ThingSpeak or something, you can do that. I was thinking about doing that, and I decided let's make this generic, show how we can do the measurements, show the hardware, and then it'll be up to the user to create that UI. So with that in mind, the first thing I want to show at the top is I'm using compiler directives, because since I'm using the serial monitor, I can't print out my average and fast measurements. So what I'm going to do is use these compiler directives to choose what I want to do. And I'll explain these more as we go through these. I also have a video on compiler directives if you're not familiar with them. But basically, by commenting or uncommenting some of these define statements, I choose between fast measurements and average measurements. So for instance, right now we're set up to do fast measurements and to look at the amps. If I were to comment this out, we do fast measurements and look at the volts. Once again, we'll see this in action in some examples, but that's to choose what measurements we want to use. Next in the code, I set up some variables to choose how we want to run our sequence where we adjust the current, the input current of the device we're testing. So I have two arrays. The first one sets the DAC value. So basically we're going to have a sequence where we set the DAC for 20, 50, and 280, and those all correspond to different voltage values. I'm not showing that calculation here, but what I'm basically trying to do is, we can see the time here too. So 350, this is in milliseconds, so 350 milliseconds, 50 milliseconds, and 15 milliseconds. So what I'm trying to do is simulate, like an IoT type profile where the device is in standby or sleep mode, it wakes up, it does some processing, and then it transmits that data and it goes back to sleep. If we wanted to, though, we could have 5, 6, 10 steps in this array. So you just adjust this array to whatever sequence of steps you want in your electronic load. If you just wanted your electronic load to be constant, let's say you wanted the input current to be 100 millivolts, you would just set this, 100 milliamps, you would just set this for one value. This number, you want it to match the number of items in the array, and you want these arrays to be equal. So remember that. So this number should equal the amount of items in the array. And then this repeat variable allows you to repeat the sequence for a number of times and then stop. So let's say you just wanted this sequence to run for 1,000 times. You would change this repeat number to 1,000, and then after 1,000 times, it'll just stop at the last setting and it'll stay there. Now, I have this repeat set to -1. If you have it at -1, that means it just repeats forever. Next is our measurement rates. So I have a measurement interval, so we can think of this as the fast measurements. If we're looking at the fast measurements, we're going to be seeing a sample every 5 milliseconds. So both of these are in milliseconds. And then we're changing our average measurement interval to 1,000, which is essentially 1 second, 1,000 milliseconds. Okay, this is a variable for tracking where we are in our arrays. These are for our timers. We'll look at that later, but basically when do we shift from one value to the next? These are tracked here. That one's tracked here, sequence start, and this one is measurement start, and this tracks our timers for our average measurements. And this is going to be used for amp hour calculations. This is a constant that's used for amp hour calculations because we're basically converting from hours to minutes to seconds. Here are my constants for my resistance values. So this is the load resistor. I want to use the exact value so when I calculate the current, I'm as accurate as possible. This value is the multiplier for my voltage divider. So I'm dividing the voltage down, but I need to convert it to the actual value. So you can see I have my R1, and you saw this in the schematic, my R2, and I use that to calculate the divider ratio, and I just take the inverse of that to get the multiplier. So I would calculate what the voltage is at the ADC and then times it by this multiplier to get it what it is at the input. These are just the ADC pins I'm using for current and voltage measurements, and then I declare two average objects. So I should mention up here I'm using the average library. So I'm using that for doing my average measurements. Why do it myself when there's already a library? And so what I do here is I have to declare with the object how many measurements are going to be held for doing a average calculation. And that's basically, I'm sure if I look in the library, it's for defining an array. So what I do here is I say, I'm going to use the fast measurements to do the average measurements. And so what I mean by that is I take how often I'm going to do an average, so 1 second, and I divide it by the fast measurement interval, which is 5 milliseconds. So basically that's going to give you what? 200 measurements each time. I hope my math's right there. But yeah, 200 measurements each time. So you want to make sure this measurement interval is, a multiple of the average measurement time period. And we'll see all this in the code. Okay, we'll start our setup. I just set the A0 pin to an output. I'm setting my write resolution to 10 bits because it defaults to 8 for the DAC. The DAC can only go up to 10 bits. And then for the measurements, my voltage and current measurement, I'm setting it for 12 bits because the default is 10 bits. I start my serial communication. I then write my first value in my sequence array. That's what I'm doing right here. And then I start both my timers using the millis function. So I'm getting what is the current time in milliseconds, and I'm going to use that for my timers. Now if we jump down into the loop, right here we have another while loop which is controlling the repeats. So you can see if, while we're not at 0, keep going. And so if we're at -1, this while loop will just go forever. If repeat gets counted down to 0, it will stop. All right, and here's our first timer function. So what we're doing here is we're saying, if timer, which is a function I have for doing the timer, which I'll show you later, and then I grab something from our timer array, in milliseconds, how long should this run? And then I take the start time. And then basically, once this is true, it means the timer is up. We increment our counter and we basically go to the next analog or DAC value. If we are above, if we're at the last one in the sequence, we have 3. So let's say we're there, we're going to set the counter back to 0 and then start over again. And then once again, then we restart our timer variable. And once again, I'll show you the timer function. We do the same thing with our fast measurements. So remember, I set the fast measurements for 5 milliseconds. We're in this infinite loop. Well, assuming we're not using repeat, but we're in this loop. We have our timer. Once it's been 5 milliseconds, we're going to push a value into our average arrays, our current value and our voltage value. And you can see there's some functions here I'm using to get those values, and I'll show those later. Then here's my compiler directives. So if I define fast measurements and if I define fast amp measurements, I'm going to print this out, which is a current measurement. And this times 1,000 is basically converting it to milliamps. Otherwise, I'll use voltage fast measurements, or if fast measurements were never defined, these won't print out. Okay, and then I reset my timer. Okay, next we go to the average measurements. So basically, if the count of the average measurements, and I'm using the average object, volt measurement.getCount, is it equal, did we finish all of our fast measurements and we're at the time where it's time to make our average measurement, we then do that. And once again, we have our compiler directives for average measurements. We print out the average voltage, we get the average current in milliamps, we print that out, we print the max voltage, the min voltage, the max current, the min current, and then we calculate our amp hours. And basically this if-else statement is printing amp hours either in microamps or in milliamps based on how high it is. And then from there we clear out our average arrays, our current measurement average arrays and our voltage measurement average arrays. And then we update our repeat variable if it's not -1. So basically if it's 0, this will stop decrementing down, and then if it is at 0, we'll basically run through this loop and we won't do anything and we won't show any measurement data. We'll just be done our sequence. Here's my timer function that I kept mentioning. So we're going to feed in the interval. So for instance, for our sequence, let's say we have 300 milliseconds and then 10 milliseconds. Well, if we're at the 300 one, this value will be 300. If we're at the 10, this will be 10. And then we also show where we started. We get the latest value. And if we're over the interval, meaning we went through the interval, we're going to return true and execute that if statement, whether it's the measurement if statement or the sequence if statement. Okay, here's some of our measurement functions. So here's the first one. We want to get, this gets voltage. So we have a 12-bit ADC, so 4095. I divide it by the ADC reading. I times it by 3.3 volts because that's our voltage reference, and it returns the raw ADC value as a voltage value. Then we have our input voltage. Now this is going to basically take a voltage value, which we'll get from here, use our multiplier, remember our voltage divider multiplier, to get what is the voltage at the input of the electronic load. And then our input current. This is basically taking a voltage measurement, which we'll get from our ADC function, and then it's using our known resistance, our load resistor, to calculate the current. And then down here is our amp hours calculation function. This basically takes whatever the previous amp hours is, because this is a cumulative measurement, so this is a global variable. We take what the current measurement value is, and we basically get what was the time period that that value was measured. We use that time, and I basically convert it to microamps, because if we don't, we'll lose precision. Convert it to microamps, and that's what I return. Okay, and once again, if you're not familiar with amp hours, it's basically a way to represent how much capacity a battery has. So if you want to make sure you're getting what you expect from the battery, you can use this measurement. And also, the battery's amp hours actually vary based on how you're using the load. So this sort of, a battery will give you some examples of its amp hours based on a static load typically. Here you can do a test with a dynamic load, and that's one of the powers of this example. With that said, let's look at our setup. All right, here's a picture of our setup. Here's my Arduino Zero. Here's the breadboard we saw in part 1. And here's the power supply I'm using in the background for my op amp input supplies. You can see the load resistor here. What you can't see is the resistor divider network for the voltage measurements is hidden right in here. And then here's my DUT. It's a single lithium polymer cell. It's advertised as a 400 milliamp hour cell. And I basically have it connected here on the breadboard, and then here is my input for the electronic load. All right, let's look at this in action. Okay, here we're back at the code, and what I'm going to do is pull up the serial plotter. So remember our sequence. This is what's loaded on the electronic load right now. So we're going to be at a very low current. We'll jump the current up a tiny bit, and then this is supposed to represent a transmit current, and these are our timing in the sequence. And so right now, I'm set for fast measurements, fast amp measurements. So I'm going to be making a measurement every 5 milliseconds of the current, and we can show that using the serial plotter. So here is our transmit. Actually, let me stop this. That'll be helpful. Here's our transmit value. You can see we're getting about at 200 milliamps. Then here's where we're set for 50. You can see, to represent we're doing some processing before we transmit. And then here's our very low level voltage where we're consuming probably, around a milliamp or so. You can see that this is kind of noisy here at the bottom. We'll talk about some ways to clear up the noise, but you can see there's some noise, definitely some noise in this measurement, but you're getting a good 10 milliamp type variance or uncertainty in this. That is the fast current measurements. Let's look at the fast voltage measurements. So what I would do for the fast voltage measurements is I would just comment this out, right? I'm going to load it onto my Arduino Zero in real time. Once again, I'm commenting out one of the compiler directives. Okay, if we go to the serial plotter now, we can see the voltage value. Now, since we're connected to the battery, if we just let this run for a really long time, we're going to see it slowly drop. One thing I'll point out is, see these little spikes here? This is essentially, I'm guessing, I'm pretty confident, this is where the transmits of the current are happening. And so what happens is there's parasitics, between the battery output, whether that's resistance or inductance or capacitance. So what happens is when the load all of a sudden pulls, the E-load pulls a lot of current, that spike of current, the voltage value of the battery drops momentarily before it recovers. And that's typically due to parasitics in the battery and in the cabling and the connection and so on and so forth. So that's why we're seeing these periodic dips. Okay, so we can look at the current profile, we can look at the voltage profile of the input. Let's do this now. Let's comment this out. And so no fast measurements. Now we're going to look at our average measurements. So I'm going to upload that to the Arduino Zero. Okay, it's uploaded. Now let's open instead of our serial plotter, we're going to open up our serial monitor. And so now we're getting those average measurements. So I'm going to turn off auto scroll for a minute. And so if we go down here, you can see we have our average voltage. The battery's voltage right now is about 3.8 volts. Average current, now that doesn't mean too much here because we know it's jumping around. We can see our max and min voltage. We can see our max and min current. And then we can see our amp hours. So we're only in microamp hours. I hit scroll again. We can see now we're starting to get into milliamp hours. Now, remember, amp hours is a cumulative measurement. So you want to run amp hour measurement, from the beginning of the test to the end of the test. You don't want to shut it off or you lose your value, but it's a cumulative measurement. All right, so that's it for the demo. We looked at how to do the fast measurements and how to do all the average or statistical measurements as well as the amp hour. Before we wrap up, I just wanted to mention some other features that could be added. And I didn't want to make this a long series, but we talked about the UI. You could do some kind of touch screen. You could do a basic LCD display that shows maybe the average measurements. You could even put this data in the cloud, which I have an example of that using a Wi-Fi chip, the Arduino Maker 1000 and ThingSpeak. This code will run on the Maker 1000 because it's a SAMD chip just like the Arduino Zero. Another thing that could be added is a calibration function. Like I mentioned, there's parasitics, there's non-ideal effects in the circuit. So the DAC output, you get close to what that value is, but you don't necessarily get exactly that value. Well, you could use the current measurement, along with a calibration function to adjust the DAC to get to the exact value you want it to be, instead of just guessing or having to compensate for some kind of error value or something like that. So that could be added. And then you also saw our measurements were a little noisy, especially the current one. So I wanted to mention here, the way you typically handle that is you add some things like low pass filtering. Like for instance, in my setup, I have a bunch of wires that could be picking up high frequency noise. So we can add a low pass filter to get rid of that. We can even use an op amp to scale the measurement, so we're using the full range of the ADC. We could add an external voltage reference. So if our voltage reference, our 3.3 volt power supply is noisy, it's going to make our measurements noisy. So you could get an external voltage reference. They're pretty cheap. That'll give you a much more accurate reference to work off of. We could do a PCB layout. So if we did a PCB layout, we could have a separate analog ground. We'd get rid of the long wires. We would have a ground plane to shield the measurements better. So those are some example things you could do to make this more finished and get better accuracy measurements. Okay, well that's it for part 2 of how to build a simple DC electronic load with Arduino. If you have any questions or comments, please use the comments section below. If you like what you saw, please subscribe to my YouTube channel. Thank you for watching.